Module 4.2, Multiple Derivatives. Objective 1, find a multiple derivative. And Objective 2, apply a multiple derivative to a real-world application. Objective 1, find a multiple derivative. To find a derivative of a derivative is called a second derivative. To find a derivative of a derivative of a derivative would be called the third derivative. Second derivatives would be denoted f double prime of x. Third derivatives would be f triple prime. Before we get into the reasoning behind needing the multiple derivatives, let's calculate a few of them using some examples. So in example 1, we are given f of x is equal to the square root of 2x, and we need to find the double derivative. If f of x is equal to the square root of 2x, then we can rewrite that as 2x to the 1/2 power. And so that would mean that f prime of x would be equal to 1/2 times 2x, and we're going to subtract 1, so it would be negative 1/2 times the derivative of the inside using the chain rule, which would be times 2. So this would be equal to, the 2 and the 1/2 will cancel each other out, which will give us 2x to the negative 1/2, or 1 over the square root of 2x. Now to find the double derivative, let's find the derivative of that. So f prime of x is equal to 2x to the negative 1/2. So f double prime of x, or the second derivative, would be equal to negative 1/2 times the 2x intact, using the chain rule, minus 3 over 2 if we subtract another 1 from the negative 1/2, times the derivative of the inside, which would be times 2. Once again, notice the 2 and the 1/2 will cancel, which will give us negative 1 over 2x to the 3/2 power. And we have now taken the double derivative. In example 2, we're going to take the triple derivative. So in this case, we start off that f prime of x, or the first derivative, would be equal to 3 times x squared minus 5 to the second power times 2x. So that would give us 6x times x squared minus 5 to the second power. So there's our first derivative. So then we're going to take this and take the derivative of this. So here we're going to have to use the product rule, which is u v prime plus u prime v. Okay, and we're going to have to let 6x be equal to u and x squared minus 5 quantity squared be equal to v. So that's going to give us 6x times the derivative of the second one, which is 2 times x squared minus 5 times the derivative of the inside, which is 2x, plus the derivative of the first one, which is 6, times the second one, which is x squared minus 5 quantity squared. To clean this up a little bit, we're going to end up with 6x and the 2 is 12x, and then 2x again would be 24x squared times x squared minus 5 plus 6 times the x squared minus 5 quantity squared. So this is the second derivative. In this case, before I take the third derivative, I'm going to multiply this stuff out so that I can do it as a polynomial, because if not, I'm going to be doing product and chain rule all within these two terms. So let's go and do a little multiplication. So I'm going to multiply 24x times x, so it'll be 24x to the fourth, and 24x squared times the minus 5, which will be minus 120 x squared, so that's going to make that one easier, plus, and I'm going to do full in here, so that'd be 6 times, that'd be x to the fourth minus 10 x squareds plus 25. And then I'm going to distribute the 6 in, so that'd be 24x squared, x to the fourth minus 120 x squared plus 6x to the fourth minus 60x squared plus 150. Now it's going to be easy for me to take the triple derivative. So I'm just going to be able to use the power rule. F double prime of x is equal to, and that would be 96x to the third minus 240x plus 24x to the third minus 120x plus, and then the 150 is going to go away. And then now I'm going to put these two together, and so that's going to give me 120x cubed, and then I'm going to put the minus 240 and the minus 120 together. That'd be minus 360x. And I have now taken the triple derivative. Objective 2. Use multiple derivatives in real-world applications. It may seem that taking the derivative of a derivative of a derivative is far-fetched or abstract, but if you actually think about the concept, it's not. Now let's look at a multiple derivative to answer a few questions in this next example. In our example, let us suppose that the distance that the Roadrunner covers as he toys with Wally the Coyote is described with the function s of t is equal to 4t to the fourth plus 2t squared, where t describes the time in seconds and s of t describes the distance in yards. So we're dealing with yards and seconds. And let's answer these questions. A, how far did the Roadrunner run in 12 seconds? B, what is the s prime of t and what does this represent? C, what is s prime of 12 and what does this represent? D, what does s double prime of t represent? What does s double prime of 12 and what does this represent? And finally, and truly above and beyond, what would s triple prime of t represent? Given the function s of t is equal to 4t to the fourth plus 2t squared, let's first go through and find part A, which is what would the distance after 12 seconds represent. So this would be 4 times 12 to the fourth power plus 2 times 12 to the second power, which would be equal to, so the first one, using our calculator, would give us 82,944 plus, and the second one would give us 288. If we add these together, we would get 83,232, and this is yards that the Roadrunner covered after 12 seconds. Part B, we need to find s prime of t. This is much easier than the first part because all we have to do is take the derivative of s of t, which would be equal to, we would have 16t to the third power plus 4t. And so this would be the derivative of s of t. In part C, we need to find s prime of t, and we're going to do it at 12 seconds. So we're going to find that we have 16 times 12 cubed plus 4 times 12, which will be equal to 27,648 plus 48, and that's going to be equal to 27,696. And this is Roadrunner's velocity in yards per second. So he is kicking it. All right, let's look at part D. The next part we need to look at, we need to find s double prime of t. So we're going to take s prime of t up here, and we're going to find the derivative of that. And so that would be equal to 48t squared plus 4, because 4t would give us 4. And so now we have the double derivative. Now, double derivative is the change of rate in the single derivative. So change of velocity, this would be acceleration. Okay, and so this would be the formula for Roadrunner's acceleration. In part E, we want to find, after 12 seconds, what is his acceleration? So this would be equal to, and we would have 48 times 12 quantity squared plus the 4, which would be equal to 6,912 plus the 4, which would be equal to 6,916. And this would be yards per second squared. So that's going to be his acceleration. And the last question we have is part F, which is, what does S triple prime represent? And in calculus, this represents what is called jerk. And it is the change of acceleration. For example, when you take your foot off of the gas pedal, there is a slight jerk when you decelerate. So it's the change in acceleration.